Hey everyone, welcome into this video on L'Hopital's rule. In this video we are going to state L'Hopital's rule as a theorem, because it is a theorem, and then we are going to prove one case of L'Hopital's rule using some tools that we developed in the last video. So let's first state the theorem. The theorem here is again named after L'Hopital. I couldn't get there. There we go, that's correct now. So it's called L'Hopital's rule. It says the following. Let's suppose that we have two functions, f and g, are differentiable, and that g prime of x is not 0. So g prime of x is not equal to 0 on an open interval containing a point x equals a. So when we say an open interval, this means an interval that the endpoints are not included. Right, the endpoints are not included. So an interval containing this point x equal to a, but possibly, it's possible, we're going to take a limit here, so it's possible though that these functions are not differentiable at a. So I'm going to write it this way, except possibly at x equals a, precisely at x equals a. All right, now we want to further suppose that we have one of a couple different cases, all right? So either the limit as x approaches a of f of x equals 0 and the limit as x approaches a of g of x equals 0, or, this is the other half, right? The limit as x approaches a of f of x is equal to some flavor of infinity, as I like to say. That just means plus or minus infinity. And at the same time, the limit as x approaches a of g of x is also equal to possibly a different flavor, right, of infinity, but plus or minus, they're each plus or minus infinity. All right, then our result, so these are the assumptions. By the way, we're talking one case or the other case. So this theorem applies to either the case where they're both 0 or the case where they're both some infinity, plus or minus infinity. All right, then the result is the following. The result's about the limit of the ratio, okay? So the result says the limit as x approaches a of the ratio f of x over g of x is equal to, actually, the limit. By the way, this would be, in the limit, this would be 0. Let's just consider this case, right? 0, if they're both 0, this would be 0 over 0 in the limit. And as we know, in a limit, you never actually get where you're going, right? So 0 over 0 is undefined if you actually try to do it with numbers, right? With the actual numbers 0. But in a limit, it just means something really small divided by something else really small. And that ratio could actually be anything. Could be anything. So that's called an indeterminate limit, right? You can't determine the limit just by looking at it because you don't know enough information about how the functions behave. And L'Hopital's rule tells us something about how we can actually interpret that, right? And it says that actually this limit, given all the criteria that we've set out here, is equal to the same number that the limit of f prime of x over g prime of x is equal to. And remember, in this case, g prime of x is not 0. The derivative of g is not 0 in this case, all right? And then here, we always have to add, whenever you define something by a limit or you state something by a limit, you have to say, provided the limit exists. Okay, so basically what this says is that if we're given a limit which happens to be an indeterminate form, so indeterminate form again means that we end up with 0 over 0 or infinity over infinity, either one of those two indeterminate forms, then L'Hopital's rule says that we can compute the limit of the ratio of those functions by actually taking their individual derivatives and taking that limit instead. All right, now you can't just do this anytime. It's very important that the functions obey the hypotheses, right? All of this stuff that I just put this little box around, this is a hypothesis or an assumption that your two functions have to obey. They have to satisfy these criteria before you're allowed to just apply this formula. So this formula, a lot of people will remember this formula, right, as L'Hopital's rule, but this formula by itself is not good enough, right? You need to also have all of the setup above. All right, so on that note, let's prove this. So let's at least sketch a proof. So sketch of proof. This just means I might not write out every single detail. But let's do the case where the limits are both 0. So the first case. So let's suppose that f and g satisfy the assumptions that we just went through, right? So of the theorem above. And let's choose the case that the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is also equal to 0. So we'll choose the case where we would get 0 over 0 in this ratio. All right, so the way that we're going to do this is we are going to write down a couple things. So first of all, let's suppose that by the way, also up here it says provided the limit exists, right? So let's suppose that this limit, f prime over g prime, let's suppose that the limit does exist. All right, and if it doesn't exist, then we just have to, then that would mean that the original limit would not exist, right? But suppose that this limit, f prime of x over g prime of x, remember g prime is not 0, right? That's one of our assumptions. As x approaches a, let's suppose that this equals L, right? If we suppose that this equals L, then what we want to do, right, then our goal is to show that the limit, the original limit, as x approaches a, of the ratio f of x over g of x without the primes. So this is in some sense the original limit that we were asked to compute. We want to show that this equals L, right? That's our goal. So I'm not assuming that. I'm saying that's where we're headed, right? So that's why this is kind of a sketch of the proof. I'm telling us what we want to do. So we want to work with this one then, right? This one. So the way that we do this is we are going to define a couple of new functions and then apply a theorem that we recently learned. So we are going to define two new functions. And they are going to be the following. I'm going to call these capital letters. So capital F of x we'll define to be little f of x when x is not equal to a, and equal to 0 when x is equal to a. And similarly, capital G of x, I'm going to do the same way. So it's equal to little g of x, whoops, when x is equal, not equal to a. So in the interval, but when x is not a, but then it's going to be equal to 0 when x is equal to a. All right, and now think about this. What's the limit as x approaches a of f of x? Well, the limits never get to the point x equals a, but they get as close as possible, right? So they're going to just operate on this. So this will be the limit as x approaches a of little f of x. They're going to be equal, right? Because again, we're not worried about precise points in a limit. We just get as close as possible without getting there. So that capital F agrees with little f nearby. But we know that the limit of this, that was part of our assumption up here, right? The limit as x approaches a of little f is equal to 0, right? Same thing's going to be true for g. The limit as x approaches a of capital G of x is equal to the same limit as x approaches a of little g of x for the same reason, which we know is 0. So at this point, we've got that f, the limit as x approaches a of f of a, big F of x is equal to 0, and big F of a is also equal to 0. So what's that mean? Well, that means that f is continuous at x equals a, right? Little f is assumed to be continuous everywhere else, and now we've built a function capital F that's continuous everywhere that little f was, because it agrees with little f, right? And is also continuous at that point x equals a, right? Just in case the little f wasn't, big F is. Same thing here, right? G of a equals 0. It's the exact same result, right? So big G is also continuous at x equal to a. All right, a couple more results here. Big F, so by the way, what we really want here is then, therefore, this is what I'm going to state here. All right, so therefore big F and big G are continuous on the entire interval. On the entire interval, let's call it I, that contains this point x equals a. That interval is the one from the original statement up here. So I didn't name it up here, right? So let's name it. Entire interval I. So there we go. There's the interval. That's the interval from the hypotheses of L'Hopital's rule. I just didn't name it before, but now we've got a name for it. All right, as we scroll back down, so we've got continuous on the entire interval, right? Look what we also had here, right? So f and g are differentiable, actually, right? They're differentiable on this entire interval. And so that means that capital F and capital G are also differentiable. And so capital F and capital G are also differentiable on I, since, why? They're derivatives, right? F prime, big F prime is equal to little f prime. Big G prime is equal to little g prime. And then at this point, right, remember, they don't have to be equal at that point, but yeah, so they're differentiable since big F prime is equal to little f prime and big G prime is equal to little g prime. Further, big G prime of x is not equal to 0 on I for the same reason, right? Since little g prime of x is not 0 on I. Okay, so what does this mean? Well, this means that Cauchy's mean value theorem applies to f and g, right? So now this is the mean value, the generalization of the mean value theorem from our last lecture video. So Cauchy's mean value theorem then applies to big F and big G and says what? Says that there exists, I need to be a little more clear here, sorry. So there is an issue with the differentiability, okay, that I should have stated, and we can't apply the Cauchy's mean value theorem yet because I haven't stated this properly. So actually they're not differentiable on I. They're differentiable on the portions of I that are on either side of the point A that we're taking the limit toward. So let's say this is our interval I, and this is our point A, right? So let's say our interval goes from here to here, right? So all we can say about differentiability, so that point, right, A is where the limit is headed. We don't know, but our definition here did not tell us that the function is differentiable on the entire interval. So something crazy could be happening, even though it's continuous. It could have a corner or something where we have this, where we added in this extra information. So we can't actually say that it's differentiable on the entire interval. But what we can say is that it's differential. These two functions are individually differentiable on this interval. So this interval is like the interval from x to a for some x in I, right? And then it's also differentiable on this interval. So from a to x in this direction, right? So whatever for any, whatever this is for x greater than a. And what we're going to do now is we're going to take a one-sided limit. So let's focus on this green side right here. So on the green side, we're going to take a limit, right? We're going to take the limit as x approaches a from the right. Okay? So what does that mean? Yeah. So I'm going to delete some of what I wrote here and fix it. Sorry. So it applies to f and g on the right-hand limit, right? On the right hand, on this one limit. So Cauchy's mean value theorem applies only on this side and then on this side separately. So we'll have to go back and talk about that in a minute. So it applies to f and g on the interval, right, from a to x. And now, what does Cauchy's mean value theorem say? So remember, we've got our continuous everywhere. We've got our differentiable on that interval right there. So we've got continuous, we've got differentiable. By the way, this continuous everywhere means that the functions are continuous on the closed interval, right? The closed interval that contains a. And that's important because that's one of the assumptions of Cauchy's mean value theorem. And then differentiable on the open or half open interval. And now it says then that there's a point in between here, right? So it says that there exists a number C between x and a or a and x in this case, such that the following is true, right? So the following is going to be what? That the derivatives f prime of c over g prime of c, the ratios of the derivatives, g prime of c is equal to the difference, f of right endpoint is x minus capital F of a, that's the left endpoint, divided by g of x minus g of a, right? But we've got a couple extra things going on here. This one is f of x, right? Because f of a and g of a, we defined those to be 0. F of a is 0, g of a is 0. So this is f of x over g of x. And on this side, this is the derivative. The derivatives here are equal to the derivatives f prime at c over g prime at c. Okay? So we've got a couple things going on here. Number one, this is equal to this. And number two, these are equal to each other. All right? And so now we can take the limit, and let's see what happens. So then the limit as x approaches a from the right of f of x over g of x, this is equal to the limit as x approaches a from the right of capital F of x over capital G of x. Why? Because, again, we already talked about this, right? These functions are equal to the lowercase functions when x is not a, and if we're taking the limit as x approaches a, then we never get to a. So these are equal. And then here, by our Cauchy mean value theorem, we get that this is equal to what? F prime of c, right? This is equal to the constant value. So the limit as x approaches a plus is equal to f prime of c over g prime of c. But c, this point c depends on the interval, right? It depends on the x. Depends on the x value. So actually, this is just like a squeeze theorem. As x moves, the point c might be somewhere in the middle here. And as x moves this way, it's going to move c with it. It's got to always be between these, right? And so the limit as x goes to a from the right is going to be the same as the limit as c goes to a from the right. So actually what we can do here is we can replace this with c, right? And so this is just now a different letter. And so this, by the way, by this formula, is equal to the limit as c approaches a from the right of f prime of c over g prime of c, which is, of course, I'll swap it out with x now just to get the notation looking right. It's equal to the limit as x approaches a of the ratio of the derivatives. So after all this, we got that the limit that we want is equal to the limit right here, right? But we said that one equaled L. Did we? Where did we say? Way back up here, right? Yeah, that one equals L. Limit as x approaches a of f prime over g prime is equal to L. And really what we care about is that these are equal, right? So, but as far as the proof is concerned, we have now shown that x approaches a from the right-hand limit equals what we want it to. So I'm just going to write it this way because this is the way that that we're going to use it, right? But they're both equal to the L in this case. Now, this is not the end of the proof, right? So what do we have to do? I think I'll leave it here. We called this a sketch of a proof anyway, so I'll leave it here. But what do you have to do? You have to then repeat the argument going this way, all right? And so you get like a c prime here, but the argument's exactly the same. You just apply the left-hand limit. You apply the Cauchy mean value theorem on this half open interval. It's still, the function's still continuous. Everything is exactly the same, except you get this little extra, I called it c prime. You can call it something else. But what you end up with then is that the two one-sided limits are equal, and so you'll get your result that way. So how you can think about then how you're going to switch this out if the limits equal infinity to start with, and basically you just take a reciprocal. So I'll let you think that one through. But basically this is the sketch. So recommended exercise, finish the proof. Finish the proof. But it's always, I'm going to put a box there, assume that we finished it. it's always good to make sure that you understand the reason behind the rule, right? Because that'll give you some intuition about the limitations of the rule, but it also gives you intuition about how the rule works and why the rule works. So this is the statement and the proof of L'Hopital's rule, and there you go. I'll see you in the next video.